Well, this is a course about energy, and one of the odd things about energy is that it's somewhat difficult to define. Uh, in one sense, we could say energy is the property of a system that is always conserved unless something comes in from the outside and changes that system. That's something we will find is a force acting from the outside, which is why we've previously had to define what we mean by force. So that all sounds sort of very vague and confusing. Maybe it's because energy is this weird thing that can take many different forms. And so we're going to take a look at some of the different forms of energy leading up to the concept of conservation of energy, which is a universal law that states that the total energy in a closed system is conserved, but that the energy can change form within that system from one form to another, as long as the total amount doesn't change. So a very simple example here, we see a skier going downhill, and at the top of the hill, that skier has potential energy indicated by the letters PE. And as the skier slides down the hill, the skier starts moving, and that is a form of energy called kinetic energy, indicated by the letters KE. And so the total amount of energy for that skier is not changing, but as the skier moves downhill, the potential energy is getting smaller, and the kinetic energy, the energy of motion, is getting bigger. Another example is the arrow. When the bow is stretched, there is elastic potential energy in that bow. And when the bow is released, the arrow then receives that elastic potential energy, which gets converted again into energy of motion or kinetic energy. So potential energy, here's two different examples of it. One is gravitational potential energy, being up high and having the ability to fall, take something and drop it. Up here, if I let go of it, I'm not doing anything, and yet it gets kinetic energy, so it must have potential energy. When it's up high, that's gravitational potential energy, or something that is springy, like a spring has elastic potential energy. So energy can be related to the fundamental forces in nature, and there are uh, four fundamental forces in nature, and then sometimes people merge some of them together. This slide just indicates three of them, the three most common, the three that we'll need to deal with in this course. Uh, One that we're very familiar with on an everyday basis is the gravitational force. Um, we're sort of used to it, but if you have the experience that I did of flying on the Vomit Comet parabolic airplane flights, uh, where you're floating, you become very aware of the gravitational force, but that makes things fall. That's a force that exists between any massive objects, and the Earth is a very massive object. And so there's a force that it exerts on other things that causes them to try to move towards the center of the Earth. The electromagnetic force we are maybe less familiar with on a day-to-day basis, but it is what controls the interaction of atoms and molecules. And in fact, the reason that I can't put my hands through each other, even though my hands are mostly empty space, if you go back and look at the sketches of what an atom has looked like in Module 1, it's mostly empty space. Well, how come I can't just push my hands right through each other? We say, oh, well, they're running into each other. The particles are hitting each other. No, they're in fact not. Nothing is actually in contact with anything else when I do this, but the electrons in the atoms of this finger are getting very, very close to the electrons in the atoms of this finger, and because they're both negatively charged, they push each other apart. So uh, the there's not actually a solid particle contact there. There's just the electrical force. And of course, the flow of electrons, we can tap into that flow and use that flow of electrical charges to do things like power devices such as air conditioners or refrigerators or electric cars. And then there are two nuclear forces, the strong nuclear force and the weak nuclear force. We're only going to be talking about the strong nuclear force, and really we're not going to have to worry too much about the details of that force, but that's the force that holds the nucleus of an atom together, the protons and neutrons in an atom, and it stores potential energy in that nucleus, which can be liberated through nuclear reactors. Gravity also exists between the Earth and the Moon. It's what's responsible for the tides, and the gravitational force depends on how far apart two things are. And so, as depicted in the slide here, it's showing that the Earth gets stretched a little bit by the gravitational pull from the Moon. And of course, Newton's third law tells us that the Moon also gets stretched. It's just that the Earth is covered with oceans, and oceans are more stretchy than rock. And so we can see that stretch a little bit easier on the Earth. And as the Earth rotates, the ocean slosh points towards the Moon as the Earth rotates underneath it. That causes that tidal bulge, the stretched out oceans, to slosh up and down the beaches, which is why we have tides. And you'll notice that the tidal bulge is symmetrical. The whole Earth gets stretched, which is why as the Earth rotates underneath there's 2 high tides a day, and takes 24 hours for it to go around. So at any particular point on the Earth is going to run into the high part of that bulge twice a day. We can tap into that energy, right? There's energy available there from that gravitational force. The tide sloshing up and down the beach, that's a potential source of energy that we could convert to some other form of energy and make use of. So there are these fundamental forces that provide different sorts of or applications or examples of energy that we can use to do the things that we need to power our lives. And most of the energy that we currently use comes from what I call chemical potential energy, and that is food, coal, oil, natural gas. That energy is stored via the electromagnetic force in molecules. And if we react those molecules with oxygen, we rearrange those atoms and molecules in such a way that some of that stored energy of the electric force gets reconfigured and liberated in the kinetic energy of the atoms and molecules that make those things up. And they are moving around quickly, which is measured as heat. And we can use that heat to do things like turn electrical generators or at a smaller scale, power our muscles. So here where it says oxidation of fuels, ultimately that chemical potential energy is really a manifestation of the electromagnetic force within the molecules. So let's take a look at some of these different forms of energy one by one. Electrical energy has to do with the flow of electrical charge. And an example here is showing a battery, and a battery has had energy put into it in order to make the battery in the first place that resulted in the positive and negative charges being separate from each other, and they can't reconnect inside the battery. But if we hook a wire up to the negative terminal and run that wire around to the positive terminal, then the electrical charge can flow easily through that wire. And if we put something like a light bulb along the path, that light bulb taps into that flow of electrical charge, and in this example, lights up. So we've got an example demonstration video showing a generator where we have these transformations of energy. Stored chemical potential energy in food gets oxidized, converted into kinetic energy of muscles, which are directly connected to the mechanical generator and causes that to move. So it has kinetic energy of the generator, which causes a wire to turn a magnetic field, which produces a flow of electrical energy through a circuit. If a light bulb is hooked up to that circuit, that causes electrons to flow through the light bulb and heat up and radiate light, and we get light energy out of the end. So there are many, many transformations of energy, but the total amount of energy in the system of this person plus the light bulb, if we were capturing that light, is conserved. So this is just illustrating how an electromagnetic generator works. We won't go into the details in this video here, but the motion of a wire in the presence of an electric field causes electrons to flow through that wire. And if we hook that wire up to a circuit, something like a light bulb or a house or a city, it takes work to push those electrons through that circuit. And so that means it takes more work to turn that loop of wire in the electric field. And you see here a picture of a large generator, and it takes a lot of energy to turn a big enough generator and a big enough magnetic field in order to produce enough electrical current to power houses, buildings, neighborhoods, and cities. So all electrical generators work on that same basic principle that somehow in the end, as you see in the middle of this slide, the turbine in the generator, I have to turn something mechanically which causes a coil of wire in a magnetic field to rotate, which produces a flow of electricity. And that could be, I could turn that turbine by burning coal to produce steam to do it, or I could do it by having nuclear materials boil water, or I could do it by having wind blow by a windmill and have that be the thing that turns the turbine. This is an example of a coal-fired power plant, and at the bottom we see the list of energy transformations. And again, we can see that the same process could be done with a nuclear power plant as well. Photovoltaic power, which we'll come to later, is a different sort of different series of energy transformations. So in the United States, where do we get our energy? On the left, you see a figure from the second edition of your textbook, and then from a few years later, from the third edition on the right. These are sources of where we get our electricity in the United States. And at the time of the second edition book, which is about 2010, 45% of that was coming from burning coal, 24% from burning natural gas, only 0.03% from solar was producing electricity. Fast forward to 2017, and the data here are only from 2015, book from 2017. You can see that the fraction of our electrical energy that is coming from coal dropped from 45% to 39%. The fraction coming from wind increased from 2.3% to 4.5%, so roughly doubled. The fraction coming from nuclear stayed the same. The biggest increase in terms of total amount was natural gas, which went from 24% to 28%. And that's basically where the drop in coal came from. And it came about because of a process called fracking, which makes it cheaper to extract natural gas from the ground. And then for purely economic reasons, natural gas became a cheaper source of fuel than coal. So the demise of coal is only to do with economics. You can see that the change in wind and solar, geothermal, all the other renewables up here on the upper left of this pie charts are negligible compared to the growth in natural gas. The final slides here describe the energy of light, and that's a form of electrical energy. Light is an electromagnetic wave, and it carries energy with it in little packets called photons. The energy that we see with our eyes, we see visible light, which is just one specific wavelength of light, which spans a very large range, all possible wavelengths. You can see the visible is just a tiny little narrow wave range of wavelengths. Redder light than what we can see becomes infrared, microwave, radio waves, cell phone, communications are all carried by light waves. Shorter wavelengths of light become ultraviolet, X-rays, gamma rays that we can't see that are very high energy. And the smallest indivisible packet of energy that can be carried by light is called a photon. And the last slide tells you how to calculate the energy of an individual photon. So as we go through the semester, we will learn how to numerically quantify and calculate how much energy there is in a particular type of energy, such as gravitational potential energy, electrical energy, kinetic energy, and so forth. And that's what's unusual about energy is since it comes in so many different forms, there's not just one equation for energy. It depends on what kind of energy we're talking about. So take a look at the example problems that are worked out that show you how to go through some of that and play around with some of those examples, and we'll go from there.